Thanks for coming. My name is Fritz Klassner. I'm the Natural Resource Program Manager with the Office of Maunakea Management. And this is another of our monthly Maunakea Speaker Series events. Tonight is actually an extra one for the month of February, which we'll get to in a minute. But the Speaker Series is a partnership between the Office of Maunakea Management, the Hilo Department of Physics and Astronomy, and the Loa Astronomy Center. And its focus is scholarship and science on Maunakea, about Maunakea and about Hawaii. And so tonight we have Dr. Elmar Schmidt from University of Applied Sciences in Heidelberg, Germany. I'm not going to worry too much about his biography and introduction. I'm going to defer to him for doing that. Other than to say, as I mentioned, this is an extra event, sort of extra talk. Dr. Schmidt was here actually thanks to the NOAA Climate Monitoring and Diagnostics Lab, which is actually on Mauna Loa as opposed to Maunakea. But nonetheless, we're happy to share the love of the mountains in Hawaii. He was here for the eclipse, which happened early Wednesday morning, which I'm assuming many of you were unlike myself and actually remembered why you were here, why your alarm was going off in the morning and didn't just kill the alarm. So he's going to talk about eclipses in general and photometry and explain what photometry is for those of us that don't know. Thank you again, Dr. Schmidt. Appreciate your time and willingness to share your expertise.
Yeah, Fritz, thank you very much for the kind introduction and the interesting information about the next talks. It just came to me that 2 or 3 talks in a month might be called the blue talks, you know, because we have all learned that 2 full moons in a month are blue moons, so that would be this would be the first of the 2 or 3 blue talks. Yeah, so we will not go far out like the huge telescopes are looking, but we will stay with our bleak companion, with our next natural celestial body, with the moon tonight. And first, a little bit about Heidelberg. It's a well-known tourist town in Germany, but it's also a hotspot of astronomy with the Max Planck Institute and the historic Landessternwarte. There's also the Astronomisches Recheninstitut that was instrumental in managing the Gaia satellite, who does a tremendous job in measuring positions for a billion of stars, actually. And of course several university departments, same as Hawaii, but historically we had observatories, but of course the conditions in Germany are not right for doing frontline astronomy anymore. So Heidelberg, as a city of 150,000, will have some 400 trained astronomers, which is a quite good ratio, but I think it will be topped by Hilo for sure. Because I think Hilo is not quite that size of the population. My lunar eclipse work fits in here somewhat, although my university, which is a smaller one, is more about teaching and with mostly applied research projects. But this special kind of science, lunar eclipse photometry, has become my topic of my later professional life. So you will learn a little bit about that and the moon as well. So a little bit on my personal background. My main professional task is teaching mathematics and physics. I'm a physicist to first and second year engineering students and at different partner universities. I was in Mexico, in France, and in China. And I also teach master students, engineering, however. My scientific interests are in the photometry, that is measuring the light, the brightness of eclipses, lunar eclipses mostly so, and also skylight. And more like a hobby, I'm also interested in various phenomena of atmospheric optics, like rainbows, which are very prominent here in Hawaii, the green flash, which is also something that you can see when the sun sets here on the Pacific Ocean. Ice crystal halos are not quite so often to be seen here, even though that high clouds can show them also because they are composed of ice crystals. And so I came into that field of photometry by a mixed private professional experience in optics and astronomy. I was working 9 years in an industry firm, and I learned about colorimetry and photometry, the measuring of light that I applied to lunar eclipses. So I feel very much honored to have been invited to speak here in this prestigious astronomical spot, the island of Hawaii. And although, as Fritz Glasner told, I was not on Mauna Kea for my latest measurement and the two before, but on Mauna Loa. Well, Mauna Loa is a little bit grumbling, as the saying is, so the alert status is on yellow. But I would say the Hawaiian volcanoes are friendly with each other, so we can also continue with talking about science from Mauna Loa. Where have I been? In NOAA's Mauna Loa Observatory at an altitude of 3,400 meters. I was visiting there in 2007, 2014, and just 2 days of that week, Monday and Tuesday nights. So, contents of my talk will be the most recent eclipse that many of you might have seen, a little bit about the basics, about my beginnings, other travels to different parts of the world, a little bit about calibration. I don't know whether there are professional astronomers or physicists in the audience. I will not go so much into the details, but we can easily talk about that later then. And as you see, the timeline goes on, and I conclude with a little bit what kind of science is in lunar eclipses. So hot off the press, that was last night's moonlight curve, and let's look at it in some detail. So this is the time, it's universal time, so the Hawaiian Standard Time plus 10 hours. England, you know, that's what the astronomers are used to use, so that's why you see daytime hours here. And this is the brightness of the full moon. The astronomers have a strange system of measuring that. The more negative, the brighter it is. It's for historical reasons. So the full moon is about -13 in brightness, and you can see over the couple of hours that it's still getting a little bit brighter, brighter, and then it plunges down into the eclipse. This doesn't look much because it's a logarithmic scale. Actually, the drop in intensity for this eclipse is about a factor of 17,000. So, as you have seen, it's gotten really dark during the total phase of the eclipse here, about the hour between 3 and 4 in the morning here in Hawaii. So, the time is running this way, dot by dot, and it's a 12-hour curve, which is something special. You could never do that in a place like Germany, so you have to go to the best astronomical sites in the world, and Hawaii is one of these. So that's really a feat. The eclipse in a diagram happened like this. The moon in its proper motion moves against the daily movement, which is just a reflection of the Earth's rotation. So the proper motion of the moon is from west to east, and it entered the shadow of the Earth coming from here to there. So the time in this sketch runs this way. So you see the moon was fully in the shadow of the Earth, the so-called umbra, which is the central shadow. As seen from the moon, it would be a total solar eclipse. I think I have a picture on that later. So a few pictures from high on the mountain. So this is Mauna Loa Observatory, Maunakea in the backdrop. This myself with one of the photometers that I used. Here it is on a tripod, directed to the moon. Here's another one for which I used this contraption as an adjustment. And this is the station manager, Daryl Kuniyuki of the MLO Observatory, who was hosting me and helping me with technical issues. So, well, you see the air is clean and you can do measurements like that in a place. So this is basic sketch of what is a lunar eclipse. You have the sun aligned with the Earth and then the moon. And the Earth casts a shadow, and if the moon goes into the central part, we have a total lunar eclipse. As seen from the moon, it would be a total solar eclipse, the sun completely hidden by the Earth. In the penumbral shadow, if the moon would be here, those parts of the moon in the penumbral shadow would always see a little bit of sun at the rim of the Earth. So that would be a partial solar eclipse as seen from the moon. Just a curiosity, the moon slowly gets farther away from the Earth. So in many, many centuries from now, the moon will not even be in the central shadow of the Earth, but in this area, and so it will not be total eclipses anymore, but ring-like eclipses. The sun will form a bright ring around the Earth, but that's many, many centuries in the future. Nobody of us will experience that. Well, this was not the scale. Of course, the sun is much farther away and so on. But this is a scale drawing of, in the right part, of the geometry of the lunar eclipses. So this is the central shadow, the umbra, and this is the penumbra, as defined by its outer perimeters. The moon has about half a degree in diameter, and here it is shown in total eclipse. The central shadow of the Earth is not completely black, but it has a little bit of red-orange light, as you have seen projected on the moon, and we'll later see where that's coming from. Here is a photographic by a French photographer composition of the umbra, the central shadow, and the penumbra. Of course, this screen cannot cover the whole range of brightness, which is about 10,000. So if you go out from here, it's getting dark in the inner part of the penumbra, and then it would get still darker than this, but the scale has been, intensity scale has been readjusted so to show the inner part. But this is the relative sizes, this sketch shows the relative sizes of the shadows. And I'm sorry, the typical radius of, wait a minute, wrong direction. The radii of the umbra and is about 0.65 degree, and the penumbra is about 1.2 degrees. And so actually there is not a full moon, because a full moon would be exactly opposite the Earth, but then it will be in the shadow and it will not be bright. So this is the fullest moon that you can get if it's just outside of the Earth's shadow, which is of course happening before and after every eclipse. Where does the orange-red light on the eclipsed moon come from? Well, it's nothing more than the dawn and dusk twilight, which is colored red and orange, which is then cast on the moon as being refracted through the Earth's atmosphere. This is one of, I think, the only true picture of a lunar eclipse as seen from the moon. And as I said, it is more like a solar eclipse. The sun is between the Earth, behind the Earth, I'm sorry. And you see that you have a ring of light. The atmosphere is illuminated from the back, and due to the long light path through the atmosphere, the light gets reddened. And this is the light that colors the eclipsed moon in orange and rusty red colors sometimes. Here's another picture showing the sun illuminating the atmosphere, also the higher parts, the stratosphere. This picture has been taken from a weather balloon. So the eclipse light on the moon is just refracted and scattered sunlight by the Earth's atmosphere, and that's why it's so red. Well, I began as a young student in school to try to determine the brightness, or rather the darkness, of an eclipse. You will see that this is generally a similar curve coming down from here and going down to a bottom during the total phase of the eclipse and going up again. Well, the moon poses a big problem in measuring its light because it has no comparison objects in the sky. When the moon is in the sky, even in the night of a total eclipse, it is always so bright that you don't have many comparison objects. Maybe brighter planets could be used, or other tricks. For instance, you can reverse a binocular, and then the moon's light will be getting diminished by a certain factor. Then you can compare the diminished binocular view of the moon with certain stars or planets. But this is, of course, not really accurate. And sometimes if you're short-sighted, I tried that last night too, so you can see the moon as a blur and the stars as well. But it actually doesn't really work well. Many people do that, and they really try hard, but it's really an amateur's method, which is okay in its own right, but actually it's inaccurate. So we come to photometry as a rescue of that situation. This is a line of instruments from Konica Minolta company, which I used for all my eclipse work. The newest one is shown here. I brought it here. We can later look at it. It just looks like a small gun here. And so I have a viewfinder, and I can center the moon, and then pull a trigger, and I get a measurement. So it looks quite simple, but these instruments are very, very accurate, and they cover a huge range. If you look at this here, it's from about 1 million candela per square meter to 1,000. So that's 9 orders of magnitude. And these instruments are really linear and also absolutely calibrated. So, but obviously nobody other than me thought of using these instruments for lunar eclipses. So that's my niche in science, and I'm happy about it. So there will be hundreds or thousands of people using these instruments for measuring lamplight and so on. And there will be other hundreds and thousands of people that are more deeply interested in lunar eclipses, but the intersection set is just me. I think so, which is sometimes not good because you have to be very careful not to make any mistake and do all the calibrations right. I would like to have a little bit of competition, not too much. Obviously, it's not so much a thing for frontline astronomy. Of course, we have to look for exoplanets and galaxies and all that. It's much more exciting than the moon, for sure. It's not joking. So, well, these instruments have been borrowed or provided for free by both Konica Minolta and by a former colleague, and this was my former company where I got a start in using these instruments. Yeah, of course, you have to calibrate the instruments. We have a little bit south of Heidelberg is the city of Karlsruhe, which has a very renowned technical university. For instance, the famous physicist Heinrich Hertz was working there, detecting electromagnetic waves in the 1880s or 90s. So they have a luminance standard, which is an Ulbricht sphere. It's a sphere with a lamp inside, and it's very accurately, it's stable, and it provides these values, and you can check your photometer like this one and then correct it. But actually, whatever I found is that they were accurate to better than 1%. But even the little deviation, I then corrected to my data. Well, this is a strange unit, candela per square meters, which is called luminance. Physicists are more used to using radians. So candela per square meters would be lumen per square meter, and steradian, which is spatial angle, and the corresponding measurement would be watts per steradian and square meter. But we don't have to deal with these details. It's just the one unit which is used for measuring light, the candela. It's actually a basic unit, but it's under fire. So many people don't want to keep it because it's the most inaccurately defined basic unit. But well, lighting is still important and big business, so we still have the candela. Okay, so much about calibration. Well, this is an older light curve which I received in 1990 in Germany. So sometimes you can have luck in Germany as well. So almost, we had high clouds in the beginning, but then once again, this kind of curve, bottoming at -3.3 magnitude, which is brighter than yesterday's eclipse and brighter than the other one that I showed before. The range is only about 7,600. Started out at the full moon at almost 5,000 candela per square meters. Well, of course, there are theoreticians that are making predictions, so it's always nice if that somehow matches, but there's no guarantee that this is the case. There can be disturbances in the atmosphere that will lead to deviations. So that was 1990, and it took 17 years to finally obtain another such data set in Germany. Well, I have to say I was very much involved in industry work, and I was raising a family, so I was not really so much on the go for every eclipse, but I tried some, and mostly the weather was not good. So this one worked out in 2007, March, and once again a picture from a friend of mine with a very good small telescope, which shows the moon in its orange-red color. And Nina was at the time a beginning physics student and was helping with the measurements at an amateur observatory quite low near Heidelberg in Germany. So what did we get? Well, at least half a light curve, which is good enough because we could see the whole range from full moonlight going down to the totality. So in this case, the intensity drop was once again about 17,000, so a little bit more than at the eclipse before. I will compare my different eclipses later then in a sketch, and you will see the relationship that mostly governs how much of a drop you can expect or measure. So what do scientists do? They write a paper. We had a talk at a light and color meeting in Bozeman, Montana in 2007, the same year. Nina, by the way, is now a postdoc. She's fully professional astronomer now, and she's a postdoctoral fellow at Caltech in Pasadena. So, well, I gave her at least a little bit of a start, but she's very smart and did a lot of things way over my head. So astrostatistics and whatever, and simulating light optical properties of black holes and so on. So quite a girl. Well, so 17 years in waiting for just 2 eclipses in Germany. So then I decided, no, that can't be. I have to travel. So I'm the crazy one that travels to lunar eclipses. You know, traveling to solar eclipses is good business, but I think not many people will travel around the world to look at lunar eclipses. Why? Well, it's in the statistics. We have in the current millennium from 2000 to 3000, we have 716 total lunar eclipses, and they only happen in about 1/4 of the Earth, or 1/3 at most. So you would have to expect, let's say, about 200 of these eclipses in Hawaii and in any other place on the Earth. So a certain place therefore only gets the chance for an eclipse every 3 to 5 years. Okay. Well, in Germany, we have about 50 clear nights in a year. That's a 15% chance, and it's a simple calculation to divide 3 by 0.15. So you would have to wait 20 years for a good another eclipse in clear skies. And this is just about consistent with what I experienced. 2 eclipses in 17 years, and one not even full in time. So if you go to prime astronomical sites around the world, well, you lose that factor of 3 because you can have any lunar eclipse because you are in the right meridian on the Earth. And in these sites, you have 200 to 250 clear nights per year. That's a 60% chance, or even better. And if you do a simple calculation again, you would have to expect a successful measuring campaign every 2 years, so 5 per decade. And that was my last decade. This screen is, yes, worked out, failure, worked, failure. So I got about 5.5 because one of these eclipses of the successes was only half. So that's 5.5 out of 8 eclipses visited, and 10 happened. So you come to a success rate of 60 to 70%. So statistic works, we can see that. Well, I want to measure 2 more eclipses after this one, then I retire, and well, maybe I continue, I don't know yet. 80,000 kilometers one way, flying around the world. This is one-way distance, and at maybe another 30,000 for conference trips. So that was quite a lot of traveling. Well, how did I come to Hawaii? Well, we this is a group photo from that conference on light and color in nature in Bozeman, Montana, and we had an excursion to Yellowstone National Park, and so here are all the guys, and this one person, Joe Shaw of the University of Montana in Bozeman, I asked him, well, there's an eclipse in Hawaii, do you know anybody? And he said, oh yes, yeah, I've been there, and I know my colleague John Barnes, and so we got into contact, and so I got invited to Mauna Loa Observatory for the first time. John Barnes was a resident scientist and station manager for MLO until just about 2 years ago. So 3 months later, after this conference, I came to Hawaii and went up on Mauna Loa, or not quite on top, but on the slope to their facility. Well, you see, same old setup. And this is a night or a day that you want to have, which is promising clear skies during the night. Well, waiting, there were some clouds and fog, but they went away. The sun goes down, the moon goes up, as it should be at full moon. And then the measuring started, and this is my first total eclipse light curve, and it's still a very good one, as you can see. Here is something which is quite not so well known about the moon. Even in the very last degrees of movement near the opposition spot, the moon's brightness increases and increases. So this is an effect that I will later talk about a little bit. So very nice curve once again, flattening out at about -1 magnitudes. So, well, I have a day or two of idle time, so I always resided in a private house of Mrs. Black here on East Lanikaula, and so here is a French engineer on the Euclid telescope. He was a student. That was in 2007, so.
Yeah.
calibration. The moon poses a lot of problems in calibrating because it's not easy to tell its brightness. You don't have comparison objects. Oh, this sentence is not complete. You don't have comparison objects to start with. Then if you look in the literature, you find, look at luminance values, you'll find anything between 2,500 and 3,700 candela per square meter once again. So what's true? The illuminance, which means the solar illuminance, for instance, would be 100,000 lux at a typical day like today, but the moon, full moon even, will only have something between 0.15 and 0.27 lux. What's true? Again, a factor of 1.8. In gray literature about photography, you will see even a bigger range. So, well, actually, the span of brightnesses is not completely artificial or erroneous. It really represents measured data. Let's have a look. There are several influences on the full moon's luminance, the intrinsic brightness of the moon. Of course, first of all, the solar distance varies by about plus minus 3.3%. That will show in the moon. If the Earth and the moon together are farther away from the sun, which is the case in our summer in the northern hemisphere, then the moon will be, full moon will be a little bit weaker. And now in the winter, when the Earth is closer to the sun, together with the moon, it will be a little bit brighter. That's an effect that can be measured and needs to be considered. Then there's a lunar opposition effect, which is incredibly strong. It's about plus 30%. I will show later. Generally, the luminance is independent from the moon's distance to the Earth. So that doesn't matter. It's you know, this band, this wall here is as wide from close and far. There's not too much of a difference in luminance. But if you have a small luminous spot, however, the farther you go away, the weaker will be the light. So we're talking now about the brightness of the moon and how much it illuminates the Earth. That's called the illuminance. And this is measured then in lux. And this, of course, varies with the lunar elliptical orbit. The moon is sometimes closer to the Earth and sometimes farther away. Just in 2 days ago, it was a so-called supermoon, was relatively close to the Earth. So this would be about 16% brighter than an average moon. So it is certain hype, which I don't like so much, but actually it is a fact, and the moon can have quite a lot of variation in brightness. So the total brightness variation for anything like a full moon would be a factor of 1.75 from minus 14% to plus 50%. So it's not a constant full moon. We have to consider that. This is a measurement I did in Germany, and it shows how the moon gets brighter. No eclipse here. In the last 20 degrees away from the opposition spot, away from a possible lunar eclipse. And you see this is a linear scale in candela per square meter, and you see that it's almost doubling. Although the illuminated area of the moon increases by less than 5%. So it would, for the average layperson, it would be a full moon, mostly so. But still, it's getting incredibly brighter. So why does that happen? Here's another picture, more complete. It shows the moon from waning to waxing half, going up in brightness. This is the reflectivity, so it's just about the same measurement. The moon reflects, typical full moon would reflect about 10.5% of light, and if it's getting closer, it could be 30% more, as we have seen. So what for an average full moon could be anything in this yellow range, and you see that you have a large variation in brightness. Eclipse. The eclipse zone would be this here. Of course, then the moon will be dropping down again, as seen from the Earth. So there is only a true full moon, as seen from a lunar orbiter satellite circling the moon. Then you really can look at full moon, which is not eclipsed by the Earth. Okay, so this opposition effect can be seen in pictures from Apollo astronauts as a brightening around their own shadow, which is in here or around the lander. What is it? Well, it's mostly shadow hiding. If you look onto, let's say, a field of lava, and if you look at an angle away from your shadow, you will see shadows cast by the stones and by the pebbles, and these will darken the view, and it will be looking quite dark there. But if you look right next to your head, you don't see any shadows, so that's called shadow hiding. And this is basically most of the so-called opposition effect, which is very prominent in the moon because it's a dry body and casts very strong shadows. There might be a certain amount of retroreflection, like in traffic signs by glassy spherules, glass spheres in the lunar soil, but this is not a prominent influence. It's a minor influence. Most of the opposition effect is shadow hiding. So it's also seen to be here on Earth, as I said. If you look on your shadow on a dry, rough surface, you will, at low sun, you will always see a little bit brighter area around your head. And if you're farther away, I don't know if that shows so well, but I think it will, yeah. If you're so far away that you don't see the shadow of the airplane, but you still see this brighter opposition spot. It's also very prominent in videos from drones, which are quite popular. You will, around the shadow of the drone, you will also see this prominent brightening. So actually, what not many people know, this is a so-called penumbral eclipse when the moon only enters the half shadow of the Earth. So a very shallow eclipse. It could never be detected by visual observers. So I tried to measure that in Germany, and I was astonished. The moon didn't get darker, even if it was eclipse here in this penumbral band here. It got brighter and brighter and brighter. What's the reason? Well, once again, the opposition effect. The lunar opposition surge is stronger than even a 42% penumbral eclipse. So the brightest moon that you can have will actually be a little bit eclipsed, so to speak. Of course, it is darker here, but the rest of the moon has become so bright that it overcompensates this eclipse effect. Well, let's rush to the end of that calibration thing here. So how did I then do it? As there is no true fixed point for the brightness of a full moon, because of the large variations, the only safe way is, at least that what came to me, is that you have to use solar quantities which are well established and not varying much, about 0.1%. The solar constant varies a little bit, but not so much. And also the sun has a very constant, rather constant luminance at about an incredibly high value of 150 billion candela per square meters. An instrument like that would be damaged. You could, of course, not use it for measuring the sun. And the astronomers, of course, once again, go up in the negative scale. And so the sun has a visual magnitude of -26.73. So that's much brighter than the moon, of course. So, well, I then came up with a model of how to project the solar luminance on the moon, and you have to do some geometric corrections. I will skip the details here, but finally you come to, or you can come, or I came to a model where I could predict and check luminances and illuminances from the moon, like here. So these are the typical full moon minimum, mean, and maximum values in candela per square meters. Geometry goes in there and all the other effects. And if you look at the illuminance, how bright it is at night in the landscape, the lux values, you would have this range of 0.2 to 0.47. Quite a huge range, once again. Well, this is just theory, so I was happy to be able to check it. There was a person, which I don't even know, but who once on space weather provided a measurement in a perigee full moon, which is supermoon these days now, back in 2010, and it was in foot lamberts, but something like that. So I recalculated. He measured 0.431 lux, and my model predicted for the geometry 0.428 lux. So I was quite confident that my model is working and I can use it to calibrate my measurements. Well, this was a lot of dry stuff, so let's conclude. There are further corrections. Of course, any measurement, the instruments are precise enough, but I have to correct all my measurements to standard air mass, which means just one atmosphere above 0 altitude in the sinus. And so for this, you use a standard atmosphere and which has an optical density which is known and can be applied. But you cannot have aerosol to do that. So my eclipse light curves are at first only air mass corrected. And for comparing different eclipses, because the moon is once further and away and the sun also, I have to do some other corrections which are trivial because they're purely geometric. And so you can compare then different eclipses, which is important also to put them together. Last thing that I want to show is the instrument is not just precise, but it's also quite linear, even at low brightnesses. So it is sensitive enough to be able to measure Venus, Jupiter, and first magnitude stars. So you can see that it's a linear scale, which is important to get good measurements. So much about calibration, so which is quite an issue, however. So we were in Hawaii, or I, in 2007. Then we come to the year 2010. This is Heidelberg in the winter, December, with Christmas market. And it's a beautiful city. It's a well-known tourist spot in Germany. But, well, not really warm. So I went to Mexico. We have a partner university in Guadalajara.
Colorado me llamo, soy señores de Michoacán. Ya hasta los más salidores al mirarme pronto se van. Traigo en mi coco una silla que es de oro, plata y marfil. Dos pistolas al cinto pa'l que quiera entrarle al redil. Que viva mi tierra, Michoacán, y denme charanda a brindar. Que Juan Colorado ya está aquí, montado en su guapo el huracán. Voy por montañas y valles en mi cuaco vivo feliz. Y en cada pueblo que paso voy dejando siempre un amor.
Well, my driver got stolen the first day. So I lost my computer, I lost my data, everything, but fortunately not the photometer that was in the other suitcase. So no, they were so friendly. I don't want to say bad things. Mexico is such a happy country and I love it, but they were so helpful. They presented me with a computer and everything worked out. And but I didn't know what to expect. You know, that's Mexican way. So we went up to that place, which is called Cabana, cabin or a camp of the university, and actually it's a prime astronomical site. It's 2,400 meters high, and the mountain is even 2,600. So if you look for another site here, that would be the place, one of the places. So this is my makeshift Mexican mounting for following a moon that goes through the zenith. I did a similar thing with one of the photometers on Mauna Loa the night before. Worked, looks rough, but worked fine. And well, that's the essence of Mexico. Everything's getting good, and that's how it was. We got one of the best measurements that I have ever done, so just only to be matched by the one that I showed in the beginning from MLO. Next stop, next eclipse, a very deep one. The moon crossing the center of the Earth's shadow was visible in the eastern hemisphere, Africa and India mostly so. So my destination was Namibia. Of course, I always look for prime astronomical spots, and this is one. This mountain here, Gamsberg, at an altitude of 2,347 meters, it is owned by the Max Planck Institute for Astronomy in Heidelberg. It's about 2 square kilometers of flat mountaintop. So they wanted to build their observatory in the 70s, but it was banned by the UN because Namibia then was administrated by South Africa, and you could not do business or science then. So it has been fallen back, and of course environmental concerns have come into the game as well. But if anybody has, let's say, $5 million to build a road, he could have a prime astronomical site. It has, I think, one of the best scenes in the world, measuring Hawaii and Chile. So, but there's only a big 75 centimeter amateur scope on top of that mountain, which is very difficult to reach. So it's a very steep road and so on. I was not on that mountain, but I was on this farm, which was good enough. And that's how it was done. Once again, my Mexican mounting here. This was my office and my room. Well, this is how it looked like, similar to the night before. There comes the moon. I always joke and say, you have to go to the southern hemisphere because that's where everything is labeled on the sky. This is not my picture, but from an Italian amateur astronomer. So that's a little bit of an impression that you have also enjoyed, probably, the night before. Once again, next measurement. See, this is going down very much because it was a deep eclipse. It goes almost to 0 magnitude, so it was really, really dark. The moon only, eclipsed moon only being so bright as a first magnitude star. Well, a little bit about Namibia. Namibia was 100 years ago, or more than that, a German colony, Southwest Africa. And so there is still a sizable German population. And it boasts Africa's only German language daily newspaper here, the Allgemeine Zeitung. This is the capital, Windhoek, has a population of 322,000. But that's about 1/7 of the population. Namibia is really a lonely place, 2 million people for an area of about 824,000 square kilometers. I think that would almost be like Texas or something like that. This is a few pictures. These are a few pictures of the Astro Farm. It's one single farm, 50 square kilometers. It's owned by one family of German Africans born there. But it's desert, or half desert, only good for about 800 cattle, or a couple of astronomers or amateur astronomers renting rooms there. So, few impressions of mountain keeper. Didn't have a telephoto lens. There should be a leopard, but I didn't need. So, once in a while. The farmer has I do in the daytime, measure the daytime sky luminances and compare it with historical data, which is quite okay, but nothing much. I was there for the lunar eclipse for sure. So this is 2 dusks on different days. Of course, you can have every once in a while also have some clouds there, but I was lucky during the eclipse night. It's a popular place for amateur astronomers. They can rent rooms there and do their observations. And this was my office. Isn't it nice view here? In my room. There is a so-called International Amateur Observatory on the farm Hakos, which has quite a few instruments. Next stop was Taiwan, because there was another total lunar eclipse, 2011. Quite a different picture, raining, even going up the mountain. Special thing about, I was in this observatory, which is on the Tropic of Cancer, and at also quite a good altitude, 2,800 meters. The one thing is, it's the only bigger observatory in the world where you have to carry your luggage the last 200 meters of altitude. So that was not so nice, because I get short breath at that altitude. So this picture was taken on my way down. On my way up, I was not ready for picture taking. So it was nice up there, but that was the only blue sky that I saw in a week. So I was having bad luck here. Weather was not friendly, so we just were hanging out, and astronomers were servicing their instruments. So, but it's a beautiful place, typically Chinese, like watercolors and so on. But the lunar eclipse was completely eclipsed by fog, clouds and rain. So this on the observatory webcam was the only thing that was to be seen about the moon during that night. However, and of course, on a day like that, it's good every other place. It was good in Hawaii, it was good in Hong Kong, and so on. That's Murphy's Law once again. But there was a guy, Samyo Fong from Hong Kong. He was visiting for doing business with the observatory, and he said, "Oh, no problem. I have a private observatory near Lhasa in Tibet, which is a couple of thousand miles to the east." And so we hooked on to his observatory through the internet, and we could at least see the eclipse and the eclipse sky. But of course, it was not good for doing my measurements. I met Savio in Hong Kong 3 years ago, and we had nice noodle dish. And traditionally, he grew up in the old part of Hong Kong and showed me around. And he's a businessman. He's building small observatories and planetariums. And see this here. This small observatory is, at an altitude of not less than 5,600 meters. So the Chinese have a prime astronomical line in the east of China and Tibet. And rumors have it that they will also launch a 20 or 30 meter telescope in the years to come. We will see. They are progressing very fast in all technical and scientific respects. And yeah, why not? So
自从和你相识以来，好像你在我的眼前永远永远不分离。青青的高山，茫茫的大海，爱你像大海那样深。当你要离别那一天，少了你在我的身边，遥远的故乡，高高的月亮，请抬起头来看看那个新月光。走了一步，眼泪掉下来，才回到我的心上人。自从和你相识以来。
Yes, this is my host, Professor Chen. And they have a good astronomy department, and they do measurements on Haleakala, sky stars, and so on. Yeah, I should. Well, back to work. Next eclipse. Once again, you see the opposition effect around my shadow here on top of the mountain. This is the Chinese radio telescope. That's an impressive hexapod structure here. Yeah, you have seen that already. Next measurement. I have never been to Mauna Kea. I wanted to go up, but the road was closed due to the wind yesterday, so I couldn't do that. So it will be left for my next visit. This is not me, although he might look like that. Tenerife Island is a beautiful place in the Atlantic Ocean. I was invited by the European Space Agency's optical ground station. They have a 1 meter size telescope there for follow-up work on their satellite missions and space debris monitoring and so on, where they are quite instrumental. And so it was just the place once again for doing another measurement. Here is Tenerife in the Atlantic Ocean off the coast of Africa. So, well, that's how it can look like in good places for astronomy. So I got another measurement, however, only half of it, because in the second part of the night, we got fog billowing over the ridge. So, but the scientific information was there because I could measure the full drop to the minimum light in the total phase of the eclipse. Well, it was also a supermoon, once again, a perigee moon, quite close to the Earth. So here it is setting after the eclipse. This is Spain's highest mountain, Pico de Teide. On that island is about 3,718 meters high. Well, I walked around a little bit on the premises of that general astronomical site. They were doing some repairs at the OGS dome. This is a nice building, like a pyramid, and it's a solar lab, and they have a heliostat, and they do helioseismology following the oscillations of the sun. Quite an interesting part of solar science. These are the big solar telescopes of Isania, that observatory. It's mostly specializing in solar work. So 3 German telescopes of different size. This is the newest one, 1.5 meter, from Kicknor Institute of Solar Physics in Freiburg. And in the backdrop is an Italian-French solar telescope. So also a very good site. This crate of eggs is actually a radio antenna for microwaves, and so they also do some cosmic microwave background work. Well, you have to relax a little bit, so some good fish on the Atlantic Ocean was concluding that trip. Well, don't tell me my curves are all the same, so I now go briefly through them. This is the African eclipse, the deep one. This was the second deepest. As you can see, it was brighter at the minimum. Still brighter, the other Hawaiian eclipse. Oh, the Mexican one is a little bit odd, should be still on top, but there's... So I look for correlations like the minimum light of the eclipse going down again here as compared to the deepness of the eclipse. This is how it is measured, how many, the ample magnitude is the maximum number of apparent lunar diameters that the advancing edge of the moon has moved inside the Earth's shadow. So it must be 1 for a total eclipse, because, whoops, what did I do? So generally you see the expected correlation, the eclipses, these are 9 eclipses, measured by myself and this by a colleague. And you see that this general trend goes downward, which as it should be. But you have variation in a place like here where eclipses were of this similar depth. It's only 1.2 to 1.3. So these residual differences are yet unexplained, and I will have to work on that. Possible causes could be the lunar albedo. The moon has a north-south asymmetry, and it's a difference whether the moon causes the Earth shadow in the north or in the south. It could be related to the solar cycle. It could be related to stratospheric aerosol or whatever. So this is open for discussion, and we must see. So once again, this light on the moon contains information about the Earth's atmosphere. For instance, there is an ozone layer in the stratosphere, and this ozone layer can be seen as a turquoise band, and it's projecting on the moon sometimes. It was not seen yesterday, but sometimes you can see it, the edge of the red part being a little bit turquoise, and this has to do with ozone, and it's it's very sensitive. Yeah, I'll be finished in quite a few minutes. So you can simulate how the light is projected on the moon. There's a colleague of mine did ray tracing calculation by assuming the Earth's atmosphere to being a ring-like lens. And so it's mostly atmospheric science that is in the measurement of lunar eclipses. And there might be relationships to the solar sunspot cycle, which is somewhat doubtful. So there's a few open questions. But of course, you can always sell it as being related to climate change and issues like that, and thus hopefully indicating the carbon dioxide footprint of my travels, as you have seen. So here is a compilation of major volcanic events, which we did not have during the last decade. But if you have a major eruptive volcano, it sends so much dust into the stratosphere that a lunar eclipse will be getting very dark. And so this is a historical record of just by lunar eclipses telling something about the Earth's stratosphere. There are some classical findings from lunar eclipses. The spherical shape of the Earth was detected this way, the relative dimensions. It was important for lunar motion and determining geographical longitude, chronology, like also solar eclipses. And so to end with a few trivia, Mr. or Mrs. Moon, you might not know that, but the moon is a man in Germany, der Mond, and the sun is a lady, die Sonne, whereas the English say the sun has got his hat on. So that's something that might not be totally well known. And in Chinese and English and most other languages, vice versa. The moon is a lady and the sun is a man, but in German it's the other way around. There's an old song.
Lady Sunshine und Mr. Moon können gar nichts dagegen tun, dass sie am Himmel sich niemals trafen, denn wenn aufsteht, dann geht sie schlafen. Lady Sunshine und Mr. Moon können gar nichts dagegen tun, wenn sie auch träumen von einem Märchen, ein Pärchen werden sie nie.
Well, so why are we doing all this? Scientists for power and influence? I think not. Because we are nuts? Maybe. There's a certain kind of nuttiness of doing something like that, of course. But my 10 cents would be, science is a celebration of the beautiness of nature. It makes us wonder about our place in the universe, and it is a truly international endeavor, and in which I had the privilege only to make friends, because you can dispute about details of your work, but it's really not anything heated like in the political theater and so on. So that's what I like about this profession. It's really the truly international adventure. So a long list of acknowledgements, all the people that were helping to make that possible. I should remark once again Christian, who provided the instrument, and Mario from Konica. These are my superiors at the university, the NOAA station heads, John D. Barnes, Kuniyuki, my Mexican colleagues from the European Space Agency, and my landladies from Hakos and here in Hilo, where I always was enjoying good time. And of course, unnamed family and friends for encouragement and support. So here I'm wearing, during eclipse night, the day before, my mother's scarf. So on a bit of a sad note, I want to dedicate this talk to my mother, who died just 11 days ago at the age of 91, fortunately, but of course it was a heartfelt loss. So what else to say? Mahalo, thank you for your attendance.
So,
sorry for being over time.
Time for questions? Any questions?
Yeah. Oh.
Yeah, Rosa?
What is an albedo?
Albedo is reflectivity. So if you have an albedo of, let's say, 100%, all the light is reflected. Yeah, I'm sorry, I did not explain that. And if you have it, let's say, by 5%, it would be black like carbon. But it is, formerly it was said the moon is black like lava. Not the case. The moon has a quite decent albedo. The moon has an albedo of about, let's say, 10, 12%, which would be like this dark gray here. So it's not really completely black, as the old saying is. And when it's bright, by the way, how much we measured the screen here with my photometer, the screen will have a couple of hundred candela per square meter. So the full moon is about 5,000. So the full moon is brighter by a factor of 20 as compared to a white projecting screen. So that's quite interesting. But albedo is reflectivity.
And one other question. You know that candelabra per square meter. What is it exactly?
No, but what's it mean?
What is exactly?
Well, the candela is a Latin word for a standard candle. You know, it's you must. It's just a standard light source, and if that light source illuminates 1 square meter, then it would be 1. So it's just a unit of brightness.
Okay,
It's a little bit odd because physicists like more like 1 per square meter and so on. But,
one last question. Up in Taiwan, I was there up in the mountains. Were you anywhere near Alishan?
I was near close by, but it was still much higher, so it was almost 4,000 meters. That's yeah. So the observatory is only a couple of miles away from Alishan, the highest mountain. That's what they have. That's location. More questions here? No?
So the moon is moving away from the Earth. Does that mean it will escape from Earth orbit at some point?
Well, maybe, but that will be a very, very long time. So it's moving away by just, I think, about a couple of centimeters per year. So you can calculate how long it will take to get so far away. But in principle, yeah, eventually other disturbances from other planets might carry it away from the Earth. That's possible. Yeah. That has happened to other planets as well. That some have caught their moons and some have lost them and so on. On very long time scales, effects like that can be happening there.
I noticed that you said the spot size of the sensing spot is about twice the diameter of the moon. Do you have to correct?
Sure. Yeah.
Okay, so you take that into account.
Actually, that's one of the minor problems that I have. This instrument is completely new for me, and I had a similar one which also had a 1 degree diaphragm, and I was then able, by comparing 2 different instruments, to tell the people from the light, from not Konica Minolta, but from Gossen, which is a similar company in Germany. I told him, well, your diaphragm is not 1 the green diameter is a little bit less. In fact, oh, yes, you know, he said that. Yeah. So I think it will be a little bit less than, because I had a maximum brightness of minus 13.3, which is a little bit too high for my impression. Even for my impression, the moon can get up to minus 13, but minus 13.33, which I measured the night before, seems to be a little bit high. So it could be that the diaphragm is a little bit smaller, and then it would go down. But I will have to check that in the laboratory, and I will have to do a calibration check with another instrument which has a smaller diaphragm, only 1/3 of a degree. So that's one of the fine spots or minor issues that you need to take care of, yeah. Because I want to talk about lunar brightnesses in the range of a couple of hundreds of an astronomical magnitude, and that's not so easy for the moon. But a good question, yeah.
Do you happen to know how much does the actual surface temperature of the moon drop during the eclipse? Do you know?
That's quite sizable, yeah. There is a lot of infrared work has been done in the past, and I'm not aware of, but I think it's a sizable drop. I think it's at least 50 degrees or more even, yeah. So that's also, it can be detected in the infrared, and imaged also, yeah. Mm-hmm.
When you're viewing a lunar eclipse,
Yeah.
is it better for you to be on like Mauna Loa, which is 14,000 feet, as opposed to the smaller mountains of like
Sure,
2,000
yeah, because you have less
feet?
atmosphere.
Okay.
On Mauna Loa, I have
Right.
only, when the moon went through the zenith, I only have about 70% of the atmosphere on top of me. But however, I have to, so I get a negative correction because all my brightnesses are standardized to one standard atmosphere, which starts at 0. So it's just a mathematical correction. But of course, the clearness of the sky on mountaintop sites is not to be matched, and it's mostly that you are above what the astronomers or atmospheric scientists call the inversion layer, the boundary layer, which is about 2 kilometers of altitude just about anywhere around the Earth. So if you're up higher than this, you leave behind mostly all of the aerosol that is in the lower atmosphere. So good astronomical work requires mountaintops for sure. That's why Maunakea, of course.
Maybe. The higher the better, maybe.
Yes, for sure. Yeah. Well, seeing there's other considerations. The atmosphere shall also be stable, which can be different on very high mountains because there are a lot of weather disturbances. But generally, the higher the better. But of course, there's practical limits. Who has maybe only the Chinese can go up to 5,000 meters or more, and people cannot actually work there. You cannot really work there without artificial oxygen as a normal person. Mountain climbers would be able to do that. So there's other logistic and operational problems that come. And then we have satellites, and which are of course clear of all of the atmosphere. So there is a balance, and typically an observatory like Maunakea would be the most that you could usually pay for, because it's getting more expensive the higher you get on logistics and support and whatever. But mountain sites are
Does the angle of the eclipse going through the atmosphere also affect the amount of reading that you get back? Because obviously we had a very low angle. Have you observed any that were higher up?
You think of yesterday's eclipse?
Yeah, it was at a low angle.
Well, it was.
Versus
You don't do that.
Yeah.
The usual step on. When I show angles on the sky in Germany, I always use.
Okay.
I understand the point.
Yeah.
This, of course, this goes into the brightness, and when it will be corrected. If the atmosphere is standard, if it's really perfect, like here, this can be easily corrected. So all my brightnesses, all the curves, they were corrected as if the moon would be
Right.
The scene is, and I would be on sea level.
Yeah.
But there is not such a place where you have a sea level atmosphere which is clear of aerosols. So it's sort of an artificial adjustment, but it's logical. So all the, if I would show you the true, of course it would be darker then. But it's corrected upwards.
Have you ever been able to contemplate Chile? Because they have probably.
Yes, I have some contacts into Chile, but Chile is sort of a logistic problem because to be at one of these observatories, they will have to charge you quite a fee. So because everything has been brought there by trucks in water and all that. So Mexico was good enough for me. So there's one eclipse next year I think in January or February, 1 year from now, which is centered on the Americas and so mainland, north and south. So I ponder going to Mexico again because I also love that country, you know, as you've seen from music and all that. Good food and you know.
I'll just say a quick word about the tetrads of the lunar eclipses.
The tetrad.
Yeah.
Yeah.
And how.
Well, lunar eclipses come in seasons like solar eclipses because the moon wanders about the solar path by ±5 degrees, and so it's rather a chance that it goes into the Earth's shadow. So it's relatively rare, but it happens predictably about twice a year in so-called eclipse seasons. The present eclipse season is January or February, and then half a year from now. So in July, end of July, there is another eclipse happening to be in Namibia, by the way. So if you have luck, you can have, and whether a lunar eclipse is total or partial, or that depends on other factors, on the precision of the adjustment. So it is relatively rare to have in 2 successive years 2 total lunar eclipses each year. That would be 4 in 2 years, and that's what's called a tetrad. We had a tetrad in 2014 and 2015, and I was here for the first of the tetrad eclipses in Hawaii, and then there were 2 more also to be seen in Hawaii. But I had a new boss and new superior, and I didn't dare asking for the money. so I said, "Rather be careful." Well, he later then funded the last eclipse of the tetrad on Tenerife, which you have seen. So I did not. I left out 2 Hawaiian eclipses. Imagine this. For me, as a 3-time now veteran. But what happened? I was watching the Maunakea webcams and thought it was bad weather. So even Hawaii can have. I was so lucky this time. I caught the 2 clear nights out of 2 weeks of bad weather. So I was. Please go to the Maunakea weather forecast board because they do an excellent job. I looked at their website every day, and it started to say, high clouds just at eclipse. But then in the very last 2 days ago, it was shifted just half a day. And so I was lucky only that in the very last 2 hours of my measurement, there were clouds coming up from the southwest. But I always had a gap here and there, so I could even complete the curve. So that was the best of luck that I ever had in all of my eclipses. Yeah. But the tetrad, yeah, that can happen too. I don't know when the next one is, but it will not be so far away, maybe 10, 15 years or something like that. That can happen. But usually you have only 3 total lunar eclipses, 2 or 3 in about 2 years at most.
So with that, Dr. Schmidt will be here for a few minutes if you want to come up and ask him questions. But again, thank you, Dr. Schmidt. Appreciate your coming and taking time to share your insight and enthusiasm for lunar eclipses.
Yeah. Thank you very much, and I wish the Hawaiian astronomical community, of course, all the best with TMT and all the other issues. If not, the Europeans have made an offer on La Palma Island, which is a beautiful place, La Isla Bonita. And or Mexico has nice spots, Baja California, San Pedro Martir. But we'll see what comes out of that. I wish you luck.
Thank you.